Let's get started with section 4.2. This is the mean value theorem. In this set of videos, we're going to talk about the mean value theorem. We're going to talk about the physical interpretation of the mean value theorem, which will lead us into a discussion on increasing and decreasing functions, and we'll finally end up with some other consequences of the previous three topics. So let's get started in this video with the mean value theorem. There are no new definitions here, but we do have that theorem, the MVT or mean value theorem for derivatives, and we want to begin with a few statements. First, about this theorem. What it does and what we will see that it does is it connects the average, also known as the mean, rate of change of a function over an interval with the instantaneous rate of change of the function at a point within the interval. So it does a very important thing. It relates the average rate of change, which we've called AROC, with the instantaneous rate of change, which we've called IROC. We are going to see that the MVT shows that there is a relationship between those two pieces. Now, this theorem first arose in the 18th century by Lagrange, where he used it to determine the distance between a function and its linear approximation. More on linear approximations in a later chapter. Later in the 19th century, it helped answer many of the questions that scientists face when they pushed the boundaries of calculus and discovered strange and unexpected effects. But for us, it's going to provide the basis for many applications of the derivatives. So applications of the derivatives are where we are in right now in chapter 4. It's where we're going through the rest of chapter 4. So the mean value theorem is a big basis for that. So here it is. The mean value theorem says that somewhere between the points A and B on a differentiable curve, there is at least one tangent line parallel to the chord AB. So take a look at this picture or diagram in the upper right corner of the slide. Here we have a function y equals f of x, and this function is both continuous and differentiable. Notice that there are no gaps or jumps, and it is a smooth function. Then we see that this function exists on an interval from A to B. And at the point where the line x equals a hits the function we have called capital A, and the same where x equals b hits the function we call capital B. If we were to draw a chord between those 2 points and calculate its slope, it would be given by the formula you see here. F of b minus f of a over b minus a. That's essentially your slope between 2 points formula. It's a y minus y over x minus x. The mean value theorem says, all right, well, if that's the case, then somewhere between A and B, then there must be a point that the slope of the tangent line is the exact same thing. That we have a tangent line and a secant line that are parallel, that there exists a point, not necessarily telling us where, but just that there exists a point such that the slope of a tangent line, aka the instantaneous rate of change, is equal to the slope of the secant line, aka the average rate of change. Here it is more formally. If y equals f of x is continuous at every point of the closed interval a to b and differentiable at every point of its interior, the open interval from a to b, then there is at least one point c in the interval a to b at which the instantaneous rate of change equals the mean rate of change. In other words, it's this formula that the instantaneous rate of change, f prime of c, is equal to f of b minus f of a over b minus a. This is the IROC, instantaneous rate of change. This is the AROC, the average rate of change. The mean value theorem says that there's a place inside that interval where those two values are equal. So before we move forward, let's take a look real quick at the hypothesis of this theorem. There are actually two pieces. We have number one, that this function must be continuous on the closed interval a to b. So there's part one of the hypothesis. Part two of the hypothesis is that we need to be differentiable at every point of the open interval a to b. So we need to be both continuous on a closed interval, and we need to be differentiable on an open interval. Let's move to the next slide, and it's more about these hypotheses. Basically, those two pieces of the hypothesis cannot be relaxed. If a function fails at even one point to be continuous on a closed or differentiable on an open, then the mean value theorem may not apply. For instance, take a look at the function f of x is absolute value of x that we have here in the top right corner. That function is continuous from -1 to 1. It's defined at every value, but it is not differentiable at every point because we know that at the corner point, 0, 0, there is no unique tangent line. We are not differentiable there. Therefore, the mean value theorem does not apply. We cannot find a point in the interior of the interval from -1 to 1 such that there is a tangent line parallel to this chord created by the segment between A and B. If you look at all of the tangent lines along the curve, and in fact, this is not really so much a curve, but it's two connected rays, there's nowhere where any of those lines will be parallel to the y=1 line that's created by the chord. Look at the greatest integer function, g of x equals int of x. Now, it's differentiable at every point in the interval 1 to 2, but it's not continuous at 2. It is a jump from y=1 to y=2. And so when we look at the chord from A to B, and then try to find a place in the interior where we have a parallel tangent line, it just cannot be done. So we want to make sure here, we are always talking about the continuity and differentiability of our function before the mean value theorem ever applies. So here's our first example. The mean value theorem is what's called an existence theorem. It tells us that there is a number c that exists, but it doesn't necessarily tell us how to find it. Sometimes we can find it with a little bit of algebra or a graphing utility, but it's the value of c that's the real importance, the existence of the value of c that's really the importance of the theorem. So here's the question. We want to show first that the function f of x equals x squared satisfies the hypothesis of the mean value theorem on the interval from 0 to 2, and then we want to find that solution c that's guaranteed by the MVT, given by this equation, f prime of c is equal to f of b minus f of a over b minus a. So first of all, f of x equals x squared. Does the mean value theorem apply on the interval 0 to 2? Well, first of all, is it continuous on the interval 0 to 2? I'd say yes, it is. It's a polynomial function. There's nothing that would mean I would have to take my pencil or pen up off the paper to graph that curve. Is it differentiable on the interval open from 0 to 2? Yes. Again, it's a polynomial function. It's smooth everywhere. And we know what this function looks like. It's a parabola with a vertex at 0, 0. There's a point at 0, 0. There's a point at 1, 1. And then there's a point at 2, 4. So there's the function and a couple of key points in the first quadrant. Next, let's find that c value that's guaranteed by the MVT. So the first thing we need to do is find the derivative of this function. So f prime of x is, well, this is easy by the power rule, it's 2x. Next, we want to find the average rate of change. So the b and the a here correspond to the first and second terms of the interval. The first point in the interval is x equals 0. The last point in the interval is x equals 2. So let's see. The average rate of change would be f of 2 minus f of 0 over 2 minus 0. Well, f of 2 is, of course, 4, and f of 0 is 0, and then this is over 2. So we have an average rate of change of 2. So now what we want to do is set those two calculations equal to one another and solve. So where is 2x, the instantaneous rate of change, equal to 2, the average rate of change? This is the I rock. This is the A rock. Well, this is an easy algebra equation to solve. We divide both sides by 2. We get x equals 1. Is that inside the interior of the interval 0 to 2? It sure is. It's here. It's right in the middle. halfway between. So let's do a little graphical interpretation. If we were to look at the slope from the 0.00 to the 0.24, would that be about equal to the slope of the tangent line at x equals 1? And I say, yeah, that's really easy to tell by graph that those two lines are parallel. Therefore, the AROC is equal to the IROC. Next up, we have an exercise from the text. This is question number 1, where we're asked to do the same thing. So first, we want to verify the MVT actually applies, and I think that's easy enough to do. Are we continuous on 0, 1? Are we differentiable on the open interval 0 to 1? We can quickly check yes and yes because this is a polynomial function, x squared plus 2x minus 1. So let's first find the derivative of this function. F prime of x is equal to 2x plus 2. Next, let's find the average rate of change. So we found the left side of the equation. Let's find the right side of the equation. So we're going to do an f of 1 minus f of 0 over 1 minus 0. Those numbers came from the interval. Here's A, here's B. So let's see, f of 1. I plug in a 1, I get 1 squared plus 2 times 1, so that's 3. 3 minus 1 is 2, so we have 2 minus. Plug in a 0 to this function, we get 0 plus 0 minus 1, so that's a negative 1. And then on bottom, we have a 1. So this becomes 2 plus 1, which is 3. 3 over 1 is 3. So finally, we're going to set these two findings equal to one another. 2x plus 2 is equal to 3. That's the IROC equals the AROC. Let's solve, subtract 2 from both sides. Now we have 2x equals 1, so x is equal to a half. Is this point in our interval? It absolutely is. So 1/2, we can even say C equals 1/2. This is the guaranteed value from the mean value theorem. Another example, this one asks us about the hypotheses of the mean value theorem. Explain why each of the following functions fails to satisfy the conditions of the MVT on the interval -1 to 1. So let's take a look at part A. F of x is equal to the square root of x squared plus 1. You might recall that the square root of x squared is actually just another way of writing the absolute value function. So this is actually absolute value of x plus 1. We could prove that by looking at our graphing calculators or Desmos and seeing that the two graphs are the same. So what do we know about this curve? Well, we know the absolute value function is the V-type shape created by the two rays, and plus 1 on the end of that function is a vertical shift up one space. So a quick and rough sketch of this graph should look something like this. And then we're going to apply the mean value theorem on the interval -1 to 1. Here's -1, here's +1. So we're looking here. So does the mean value theorem apply? First of all, is the function continuous on the closed interval? And I say yes, it is. There are no jumps, no gaps, no vertical asymptotes, nothing really about the behavior of this function that's in question as far as continuity goes. Next question, is it differentiable on the open interval -1 to 1? And I say no, this function fails because look at the point 0, 0. That's a corner point, and we know that corner points are not points on graphs where we can differentiate or where we can draw in a tangent line. So that's why this function is not differentiable. We'll even write that out here. It's not differentiable at x equals 0. Now let's move over to part B. Here's a piecewise defined function. To the left of 1, we have the rule x squared or x cubed plus 3. To the right and at 1, we have the function x squared plus 1. So the first question for us now is, can we, not differentiable, is it continuous on -1 to 1? So everywhere to the left of 1, which is going to take care of almost all of this interval, we use the rule x cubed plus 3. And that's a polynomial. It's both continuous and differentiable. But right at 1, we change rules and we move from x squared or x cubed plus 3 to x squared plus 1. So I really am interested in the continuity at 1. Are we continuous at x equals 1? Because if we're not continuous there, then we're not continuous on the fully closed interval. So let's check. let's go with the definition of continuity at a point. We want to check the limit both the left and right side of 1. So the limit as x approaches 1 from the left, we would use the function rule x cubed plus 1, and this would give us a value of 1 plus 1, which is 2. Then the limit as x approaches 1 from the right is using the rule x squared plus 1. Oh, excuse me, I messed up in the first part, so I need to go back with my eraser. This is not x cubed plus 1, it's actually x cubed plus 3, so we need to change that around. So x cubed plus 3, that's 1 plus 3, that's actually 4. Now, the limit as x approaches 1 from the right, we've got x squared plus 1, so there's our 1 plus 1, and that equals 2. And since these two values, 4 and 2, are not equal, the two-sided limit does not exist. We could say the limit as x approaches 1 two-sided of f of x does not exist. And because it doesn't exist, this function is not continuous at x equals 1. And that's actually the answer here. The mean value theorem doesn't apply because this function is not continuous at the right side of that interval. And remember, the hypothesis of the MVT is we wanted continuity on that entire closed interval. I'm going to leave exercise 3 to you or for some class time. Let's move on to example 3 where we're going to apply the mean value theorem. Here's a function f of x is equal to the square root of 1 minus x squared. That's a familiar function to me. It's a semicircle with a radius of 1. So I'm going to do a rough sketch here, and we've got 1 all the way around, and then our semicircle this way. I encourage you to graph that on your calculator or in Desmos to verify that I'm right here. So here's a point, -1 comma f of -1. So here's -1. If we plug -1 into this function, we get 1 minus a -1 squared. So that's 1 minus 1, that's 0, root 0. Yeah, that's where I thought it was going to be. That's A. Next up is B, 1 comma f of 1. That's going to be over here. You can verify that. 1 minus 1 squared, so 1 minus 1 is 0. There's B. Find a tangent to f in the interval -1 to 1 that's parallel to the secant AB. So let's start out with the secant AB and find that slope. So MAB. So that's going to be f of -1 minus f of 1 over -1 minus 1. That's going to be, let's see, f of -1 we said was 0 minus f of 1 is 0 over -2. This is a slope of 0, and I think that makes good sense. We notice here that if we were to draw in that secant, then the slope is, of course, 0. That's a flat line or line segment. Next, we want to find a point inside the interval -1 to 1 that's parallel there. Well, I know since this is a semicircle that at the top of that circle, I have a horizontal tangent. That's going to have a slope of 0 as well. So m equals 0 here, and that's at the point 0, 1, 0, 1. So we want to find a tangent. Well, that tangent, we're going to say the tangent line at 0, 1, and we can even give the equation is y equals 1, and that's the parallel line there, y equals 1. I'm going to leave exercise 9 in the book for you as well, or we might do it in class or another YouTube video, and that takes care of the first piece of the mean value theorem.